Hello, this is Jack Jackson. In this next several videos, we're going to be talking about some connections between probability and statistics and calculus. And there's a lot more about probability and statistics in my playlist on statistics. Unit 3, continuous probability, relates very much to what we have here. In fact, I have links to some of these and have some of these videos included in this playlist from my statistics class, but there are a lot more of those in the statistics class, and if you have access to my Google Drive, then you can find the PowerPoints there as well that correspond to those videos if you look under my statistics course. So when we're moving from the discrete to continuous probability distributions, we have to modify our concept slightly to account for the continuous nature of the data. And what we do is what we've been doing all semester. We apply the calculus concept of the limit to the concepts of discrete distribution so that sums become definite integrals. So we're taking to the limit one more time. So for continuous distributions, they're going to be, well, continuous are discrete distributions. We have two types of functions associated with the distribution. We have a PDF, a probability density function, and a CDF, a cumulative density function. And for continuous distribution, the probability density function, the PDF, is going to be a curve so that the areas under the graph represent probabilities, and they also represent proportions. So in a continuous distribution, the probability that the random variable x equals a specific number is 0, but positive probabilities are assigned to intervals for x. So for example, the area under the graph of the PDF from x equals 1 to 2 and above the x-axis represents the probability that a randomly chosen item will have a x value that's somewhere between 1 and 2. It also represents, another way to say this is, a proportion or percentage of the population that has a value between 1 and 2. The total area under the PDF curve is always 1, and the PDF curve then can be used to compute probabilities by finding areas, which of course is going to involve integration. The PDF is needed to compute the mean, variance, standard deviation, and skewness of the distribution, which we'll talk about a little bit in a later video. The cumulative density function, CDF, on the other hand, turns out to be an antiderivative of the PDF. And what it does is the output of that function, the output of the CDF, represents the cumulative probability to the left of that input value. And we can also use the CDF to compute probabilities, but the CDF can also be used to compute inverse probabilities. In fact, we have to have the CDF if we want to compute inverse probabilities. In fact, the CDF of the two is probably the most useful overall. Now, we have certain characteristics of continuous probability distributions, and that's what we're going to be dealing with here. The calculus comes into play when we're dealing with continuous distributions. So let's talk about what characteristics the function or the graph of the function would have for a PDF for continuous distribution. Basically, there's two main things that it has to have. First of all, the output of the PDF function has to be 0 or positive for all real x. It is never negative. So the graph is either on or above the x-axis. And we also have that if we integrate from negative infinity to infinity the PDF of the dx, we get the entire area, of course, between that graph and the x-axis, and that area has to be 1. Okay, the probability that something happens is 1, and that's the total probability, okay, total area. On the other hand, the cumulative density function, the CDF also is greater than or equal to 0 for all real numbers x. So likewise, it is also a graph that is on or above the x-axis. But it has a couple other interesting characteristics. The limit as x goes to negative infinity of the CDF of x must be 0, and the limit as x goes to infinity of the CDF of x is equal to 1. So on the far left, the CDF of x either is the x-axis, it's a horizontal line or part of a horizontal line, or it's approaching that line, the x-axis, asymptotically. Okay, so specifically on the left side, it's the x-axis itself, or is approaching it asymptotically. On the right side, the CDF is either the horizontal line, y equals 1, or it is approaching that line asymptotically. CDF of x is actually non-decreasing and continuous. So we have a function that's basically starting at 0 on the far left, ends up at 1 on the far right, and it increases in between. It may actually be level for a while, but it never goes back down. So once it goes up some, it continues to go up and ends up at 1 when it starts at 0. The CDF of x is actually a continuous function, and that's why we call these continuous probability distribution, is because the CDF is continuous. The PDFs oftentimes are continuous, but oftentimes they're not continuous. Sometimes the PDF will actually be on the x-axis for a portion, and then we'll actually have a jump discontinuity to some other part. And any parts, though, that where the PDF is actually equal to 0 can more or less be ignored. Because why? Well, because we're interested in probability, which is interested in area, and there is no area between the x-axis and itself. So when the PDF has a value of 0, that's really kind of a part of the graph that we're really not interested in at all. Alright, so well, that's all well and good explaining what characteristics these graphs have, and any function that has the characteristics that I set out for a CDF is a legitimate CDF for some probability distribution, and the function that has the characteristics I set out for the PDF is a legitimate PDF for a probability density function. But what does this have to do with reality? Well, in reality, these graphs represent probabilities in two different ways. So on the PDF, probabilities are areas on that graph. Okay, so the x's or inputs are values of the random variable, the thing that we're measuring, whatever it might be. It could be lots and lots of things. But areas then are probabilities, not y values, but areas. So that specifically the area under the PDF curve and above the x-axis gives a probability. So if we want to find the probability that that x is less than a, or less than or equal to a, and that's the same probability, by the way, in a continuous distribution, then what we're doing is we're integrating the PDF curve, PDF function from negative infinity up to a. And if we want to find the probability that x is greater than a, we're integrating the PDF graph, or the PDF curve, the PDF function, from a to infinity. And if we want to find the probability that x is between a and b, we're integrating the PDF function from a to b. So, for example, this last one gives us an area under the curve, bounded on the left by x equals a, and on the right by x equals b, below by the x-axis, and above by the PDF curve. That area represents that probability. On the other hand, the CDF probabilities are actually vertical distances. So specifically, the y value of the CDF, which is of course a vertical distance from the x-axis, is actually the cumulative probability. That's what the C stands for, cumulative density function. And it's the cumulative probability. That means it's the probability to the left of the input. So if I want to find the probability that x is less than a, or the same thing, the probability that x is less than or equal to a, those are equal, and that is actually the CDF of a. That is the output of the CDF function when we input a. So if I want to find if I have the CDF formula and I want to find a probability to the left, it's real easy. Just plug in the endpoint there on the right end of the probability that we're looking at. Stick that in the formula. Output comes the probability to the left. On the other hand, if we want to find the probability that x is greater than a, we see that that's 1 minus the probability that x is less than or equal to a, so that is 1 minus the CDF of a. And if we want to find the probability that x is between a and b, then we find the CDF of b minus the CDF of a. Now this should suggest the fundamental theorem here to you. Notice that if we integrate PDF of x dx from a to b, then what we get is the antiderivative at B minus the antiderivative at A, and that's the probability from A to B, and the probability A to B is the CDF of B minus CDF of A, and so in fact the CDF actually is an antiderivative of the PDF, and the PDF is the derivative of the CDF. So these functions, the PDF and CDF, have a derivative-antiderivative relationship to each other. Okay, now I have several videos on statistics, one of which I have following this in the playlist, talks about continuous and discrete distributions and how we go from the discrete distribution to the continuous, what happens. And I'd like you to watch that one, but on this video, it makes use of this chart here and talks about this. But I want to continue this video just a little bit more by talking a bit about specifically about the continuous distribution side and how this part relates to calculus a little bit. So, for example, this is a graph of a particular PDF function, and if we get an area here like this represents a probability, in this case from 0 to 2. Okay? And so that gives you a probability, and of course to find that we're looking at an integral. So if we want to find the probability that x is in the interval from a to b, then we integrate from a to b the PDF of x. The probability that x actually equals a specific value is 0. Maybe I can explain that. It's a weird kind of result there, but if I explain it this way, say what's the probability that x equals 1? Well, you're talking about picking one value out of infinitely many values. That is going to be a probability of 0. Another way to think of it is in terms of these areas. When you're saying x equals 1, that's actually a vertical line segment here. Vertical line segment may have some length, but it has no thickness. So there's no area there. If there's no area, then there's no probability. Well, let's see, what else do we have here? Okay. I think I've already said most of this stuff. So let's look at an example here in this graph that you see right here. See a red graph and a blue graph. The blue graph here, if you can see my cursor moving around, you see where I'm looking at in the right column here. The blue graph is the example of a PDF curve for a particular distribution, and the red graph is the corresponding CDF. Now look at the characteristics that we talked about. The PDF is on or above the x-axis everywhere, and that total area underneath there is 1. So these things are actually pretty small in the big scheme of things. That whole area is just one unit, one square unit. Now that's the PDF is the blue one. Now the CDF is also, they both have an asymptote, in this case of 0 on the left. Same limit is there of 0. The limit is going to be 0 on both sides here for the PDF. And the CDF then increases the whole way, and it of course levels off to an asymptote, which of course is always 1 there. And so we see an increasing function for the CDF. Now the basic relationship between these two things is this. If we're integrating the PDF from negative infinity up to a particular number, let's say 4 right here, you take this vertical line segment here at 4, and you take the area under the curve to the left, and that represents the probability that x is less than 4. If you take that same value of 4 and you go up here and find the y value on the CDF, that y value is the probability that x is less than whatever I said, 4. Okay, so that vertical distance from the x-axis to the curve, or in other words, the y-coordinate of that point, is the probability to the left on the CDF. On the PDF, the y values are not probability, areas are probabilities. Okay, and what about if you're trying to find the probability between 2 points, between A and B? So on the CDF is the red one here, and the PDF is the blue one here. This blue graph actually is 0 on the left up to this point right here. A is 3. And from 13 here to the right, it's also 0, so it's actually on the x-axis there and there. And in between we have 2 line segment pieces. So this is actually made up of 3 parts of three lines, two constant functions, two linear functions, pieces, all put together as one function. And that's the CDF. So the antiderivative of that would be, well, antiderivative of 0 function is a constant function. So the constant function is 0 here. So the blue and the red graph are on top of each other here from negative infinity up to 3. And to the right of 13, we've gotten all the area here already. So the cumulative density is 1. Okay, and so that's a horizontal line at 1. Of course, notice the derivative of those horizontal lines is 0. So that works out. The antiderivative here of these linear pieces is quadratic. So there's a little quadratic piece here, and they're kind of meshed together right here above where this sharp corner is, and another quadratic going concave down here, one up here, one down. But in any event, we ended up with a nice continuous function, and whose derivative is the blue function here. So the derivative of the CDF is the PDF, the antiderivative, and antiderivative, specific one, of the PDF is the CDF. Now let's look at an area, or look at a probability from A to B. So if A is, say, where this vertical line is here, that's x equals A, and where this little vertical line segment is, that's x equals B, then the probability that you're going to end up with something between there can be seen two different ways on these two different graphs. On the PDF, you're looking at this area, this little trapezoid region, and that area is the probability. That's how you see it on the PDF graph. On the CDF graph, you see it as a vertical distance. So the y value here at the right end, at this value, is the probability to the left of that. The y value here is the probability to the left of that one. So the probability that it's between is the difference in these two probabilities. So it's the difference in these two y values, which is this vertical distance between these 2 points, or in other words, the distance between these two lines here, or you could see it as a little line segment on the y-axis over here if you want, or over here, anywhere in here. And so we see that on the CDF graph, the probability is actually a vertical distance, a difference in two y values. It's just CDF of B minus CDF of A. And once again, you should recognize that as the fundamental theorem, because the CDF is an antiderivative of the PDF. We've just found the antiderivative, evaluate the endpoints. That's the fundamental theorem of calculus at work right there. So once again, we have this idea that the CDF, when you take the derivative, you get the PDF. And to get the PDF, you integrate, you take the PDF and integrate from negative infinity to x, you get the CDF. Okay, sometimes we're interested in what are called inverse probability problems. Rather than computing a probability, we'd be interested in an inverse probability. In an inverse probability, say up here, we want to know an x value so that the probability to the left is a given thing. Well, in this case, the probability to the left is a given value. Let's say this value right here. We could draw a horizontal line and see where that crosses the CDF, bring that down and find the x that goes with that, and that's the x value we're looking at. So I call that an inverse probability because in this case, you know the probability and you're trying to find the x value. You know the cumulative probability, let's say, and you're trying to find the x value that goes with that. That's an inverse probability type problem. A probability type problem, the backwards from that, is where we know an x value and we want to find, say, the cumulative probability or some other probability associated with that. Probability to the left or to the right or between two numbers. So finding the median of a distribution is an inverse probability problem. The median is a value, we'll call it m here, so that the probability that x is less than m is 0.5. So it's the value here on the graph, wherever it might be, so that the probability to the left is a half. So that would mean the area to the left under the PDF is a half, or it would mean that the y value on the CDF is a half. So we could find that by taking wherever 0.5 is here on the y-axis, draw a horizontal line across from that, find the x and bring it down, and that would be it. Okay, looks like it's around here. I guess it's 0.5, so somewhere around in this area right here would be the answer in that particular example. All right, we also have a couple things else that we may talk about. One is the mean. The mean is the arithmetic mean, or the mean, the average, the center. Is basically, in the discrete case, if you look, what you're doing is you're just adding up the values and dividing by how many you have. Good old average that you've done many times. If you have multiple points with the same that occur more often, then you're essentially multiplying by their relative frequencies, which are their probabilities, and adding those up. And so that's what we do in the discrete case. In the continuous case, this sum, which is a capital sigma over here for sum, becomes the sum over here in the continuous case, which is an integral. So what we do is we use the letter mu for the mean. The mu is also known as the expected value of x. If you want to find the expected value of something, you take that something and multiply it by the PDF function and then integrate over the entire domain. So if we want to find, so what does mu measure? Mu measures the center of our distribution. If you're changing mu, you're just sliding this thing horizontally, translating it. Now the variance, we use the lowercase sigma. This one over here is uppercase sigma for sum, but the lowercase sigma is right here. And that sigma is something we call the standard deviation, and sigma squared is something we call the variance. Standard deviation, variance, both measure the spread, how far out things are from the center. Okay, and so we define that to be the expected value of x minus mu squared. So what you do is you, of course, take x minus mu squared, multiply that by the probability, and then integrate it from minus infinity to infinity. We can also measure skewness. Skewness is the expected value of a z-score cubed, which, in other words, it's the expected value of x minus mu over sigma cubed. Notice back here for variance, you must have figured out what mu is before you can start working on this. For skewness, you have to figure out what both mu and sigma are, the mean and standard deviation, before you can figure out skewness. And so what you get here is you take the x minus the mu over sigma cubed times the PDF of x, that shouldn't have the sub k, and we just integrate that with over all x's from negative infinity to infinity. And skewness measures deviation from symmetry. So if skewness is actually 0, then the PDF graph is perfectly symmetric about x equals mu, about that vertical line. So as a vertical line symmetry. If we have something that's say the skewness could be very positive, for example, and then we would kind of have a long tail off to the right. The skewness is negative; it kind of has more of a tail off to the left. And there are many different kinds of distributions. Some that are discrete, some that are continuous. In particular, the normal distribution is probably the most important one that you would study about in a statistics class. So now, again, I refer you back to this video that's going to talk a little bit more about comparing the discrete and continuous, but think about how what we're doing over here is a lot of this is to deal with derivatives and integrals, particularly with integrals. And then down here we have some questions in the notes that talk about some of this same stuff that's written out. And most of these things are covered in these other videos. And this second video here from statistics talks about using the CDF to compute probabilities and inverse probabilities. And you will see some examples of this sort of thing in the notes. Here's some examples of what the CDF might look like. There's an example as well. And we can do some calculations, and it shows a few examples here of how you can see probabilities both on the PDF and the CDF. Here's an example where we're given the CDF, and we compute some things here. It shows you how to use your calculator to help with that process as well. Lots and lots of examples of this are in these other videos. Okay, so I think we're going to leave it there. Well, actually, there's going to be a video here that talks about how to use the calculator, and then so I'll have you watch those 3 statistics videos, and then we'll come back and pick up another calculus video in a minute.